Okay. Yeah. Can you hear me well? Okay, so my talk is titled Index for Black Holes in n equal to 2 Supergravity. This is a supergravity kind of talk. I hope I will be able to convey the overall picture. And this is some project I did with Subbu from Munich, Shanmuga Priya, who is at ICTS, and Ashok Sen at ICTS. Okay, so the way I have organized this talk is this first few slides I will just tell you what the problem is, and then I will give you various pieces that we have put together to solve that problem. Okay, so here I start. So arguably one of the biggest successes of string theory is the statistical mechanical explanation of a class of supersymmetric black holes. And typically what one does is that one considers a supersymmetric compactification of type 2 or heterotic theory, and at weak couplings the microstates are bound states of branes and strings, and for these states one computes some supersymmetric index. Strominger and Rofa did this in the late 90s, and since then there are thousands of papers generalizing, discussing various things about this. So in this subject there are many beautiful results, but there are two beautiful results from the supergravity perspective. And first is the role of the higher curvature terms. So this was first analyzed by Maldacena, Strominger and Witten, and then in a very long series of papers by the Dutch group. What they find is that if you add certain class of supersymmetric higher curvature terms to the supergravity Lagrangian, then the corrections due to these curvature terms precisely match with the microscopic entropy. Okay, and this setup was taken one step further by Dhabolkar in 2004 and others, where they showed that one can compute using these higher curvature terms the entropy of what is called the small black hole, which has zero area in the two derivative theory, but it gets corrected in the higher derivative theory, and this was done by embedding the black hole into n equal to 2 supergravity. Okay, so these results are all based on the attractor mechanism, because now there is a new attractor mechanism. I am calling it the old attractor mechanism. What one does is that one takes a supergravity theory, makes the claim that black hole has a near horizon geometry which is ADS2 times S2, then consider embedding of these black holes in n equal to 2 supergravity. A formalism is developed. The formalism is based on what is called the superconformal tensor calculus, and one develops a very complicated supergravity Lagrangian with the specific higher derivative terms, and one computes the Wald entropy with these Lagrangians, assuming the ADS2 times S2 near horizon geometry, and one finds those two results that I mentioned in the previous. Yeah. Only a special class of terms are known. The superconformal tensor calculus approach only allows you to add certain class of terms. There can be other classes which are not known how to do. Yeah.
When one claims equality with the microscopic, can't you use some particular?
There is not a very good understanding as far as I understand, but there is some heuristic arguments that why the other terms do not matter. Okay, so when one does all these calculations, one finds this famous formula. So the BPS entropy with the higher derivative terms is given by sort of the two derivative answer first. So this is the central charge function which is evaluated at the horizon, and then these are sort of the corrections. The corrections are given by this prepotential function which captures the Lagrangian. The prepotential function has this field A, and this field A captures the higher derivative terms, and what this subscript means that one has to take a derivative, like very much like the derivative of the Riemann tensor that Nilay talked about. One has to take a derivative with respect to the higher derivative term, and one gets the microscopic answer. So these are the results which match from the microscopic side. Okay, so now so all these calculations were done in the late 90s. Maybe you can say by 2001 there was a clear understanding of how these things work. Okay, so more recently a method for computing index directly on the black hole side has been suggested. This is done by these authors. in last few years. Several authors have used this method to test index equal to degeneracy by comparing the index on the macroscopic side and comparing it with the microscopic side. Ashok and people from ICTS have written a number of papers on this. The question we were interested in is, can we derive the general classical formula mentioned in the previous slide using this new formalism? So can we use this method of these authors to compute directly the index on the black hole side and see whether that index matches with the formula?
Sorry, are you going to explain this new method?
No, actually, there is really no time.
No time.
Yeah.
Just very quickly, this is some development on Ashok's earlier work of doing a kind of, what is it, CB expansion of determinants and all that, or it's a totally different track?
No, so earlier Ashok had this idea that quantum entropy function where the full entropy can be computed using near horizon geometry. So in this new approach, the idea is that the full index can be computed using asymptotically flat geometries. And they propose a path integral for computing the index, and saddles for the path integral will give the classical index. That is the complex saddle. Yeah.
And it doesn't use the Schwarzian or super Schwarzian?
No. These are all supersymmetric. Everything is supersymmetric.
No, there is a super Schwarzian analog. It doesn't use that?
No. Yeah, black holes are zero temperature, so everything is at.
Okay, I see.
Yeah. Okay. Complex angular momentum. Yeah, I will come. I will come to that. Yeah. Okay, so this is the setup. This is what we want to do. Okay, now in order to do this, we need to find saddle solutions that correctly capture the charges and the boundary conditions dictated by the path integral that these authors have proposed for computing the index. What this formalism says is that the mass of the saddle should be equal to mass of the BPS black hole, and the saddle rotates in certain ways. This rotation gives rise to the non-zero temperature, which is what allows you to do the calculation in the asymptotically flat region. Now the walled entropy for this saddle added to the walled entropy, this angular momentum, should give you the BPS entropy. So the previous papers in 2001 and so on, so they gave the formula for the BPS entropy. The project is to calculate the walled entropy for the saddle solutions, calculate the angular momentum for the saddle solution, and show that the two things add and give that famous formula. That is what we want to do.
So the saddle is the one which is this omega, which is
yeah, this has this beta omega equal to 2 pi I condition, and it is rotating.
and
So
that's true even in the higher derivative.
yeah, we will argue all of that. Yeah.
Just to make sure, of course, there's no real angular momentum in this solution, and no J is measured at infinity.
No, I mean the saddle solutions are complex. They are not smooth in the Lorentzian sense. They are smooth in the Euclidean sense. In the Euclidean picture, they do have angular momentum.
The original Lorentzian black hole did.
Yeah, original Lorentzian black hole is non-rotating. Yeah.
And just last thing, with this imaginary J and so on, is there any sense in which you have a Schwarzian-like description in the near horizon, or you don't care, but what's it?
Yeah, I will not be able to answer that question. Yeah, most likely no. Yeah. Okay, so the question is, can we compute the left-hand side of the formula I showed and show that it is equal to this for general n equal to 2 supergravity with all these things included? And the answer is that yes, we are able to do this, and this is what is reported in our paper. And the aim of this talk is to explain how this is done. It brings together many technical pieces, and I will just explain how those technical pieces are organized and how we use them. I can only give an overall picture because it's really complicated. Okay, so this is the organization of my talk. So I will spend just a few minutes telling you what this n equal to 2 theory is. Then in February 2024, Chen, Murthy and Turiachi wrote a very nice paper which gave us very useful insights into how one can go about doing this calculation. But this insight was not enough. One needed to do a lot more. And this is where I will explain what I call the off-shell black holes. And this gave us some hints for some sort of equivalent localization is happening. And then we were able to make this precise using some supergravity analysis of these authors and we'll put everything together. Okay, so this is roughly how this is. Okay, so let me say what this theory is. So n equal to 2 theory is the theory of interest, and this was constructed by these authors using the so-called superconformal tensor calculus. It's good that the doors are locked, because as soon as people start talking about superconformal tensor calculus, people start leaving. Yeah. Okay, so this formalism provides an off-shelf formulation where one can include a particular class of curvature square terms which are encoded in what is called the Weyl multiplate. Lagrangians are constructed out of chiral multiplates, and an important aspect of this whole technique is that one should be able to go back and forth between various multiplates. So if you give me Weyl multiplate, I should be able to construct a chiral multiplate out of it. If you give me vector multiplate, I should be able to construct chiral multiplate out of it, and so on. So one should be able to convert into various composite multiplates, and this whole thing is called the multiplate calculus. Okay, so this one goes through this process. It's a complicated process, and one finds this very cumbersome looking Lagrangian. It has many f's. We don't need to know the definition of all these things. It is really not possible to give me the definition of all symbols in this presentation, but this is the kind of Lagrangian. So here is this the Ricci scalar. So this is one term. Here is another Ricci scalar, and then there are many a hat terms. These are the terms which will give rise to higher derivative corrections. Okay. So now we take the variation of this action with respect to the Riemann tensor to get the Wald entropy. If we just blindly compute this derivative, this is the kind of terms you will get. And the question is, can we evaluate this on the saddle solution? That is the, yeah.
Many f's. So the curly f here is the photon, is it correct? The one with the I index.
Those are the vectors. Yeah, those are. Yeah, I mean the curly f's are the vectors. Yeah. Okay, so now the problem is we do not know anything about the saddle solution, because saddle solution is some rotating black hole in a higher derivative theory of gravity. We know nothing about this solution, so how can we go about doing this calculation? So the previous calculation is just taking the derivative of that action, but now we have to evaluate this on this saddle solution, which we do not know anything about. Okay, so this is where this paper comes in. So Chen, Murthy and Turiachi in February 2024 studies aspects of rotating black holes which will eventually serve as saddle solutions, including higher derivative corrections. So the motivation for their paper was slightly different from what we were doing, but what they did is that they looked at what is called the two-charge black hole. This solution is singular at the poles in the same sense that the two-charge supersymmetric black hole is singular at the horizon. And what they showed is that the higher derivative terms play an important role, and they argue that the higher derivative terms give rise to corrections which make the solution smooth at the poles. So this calculation was sort of like the version of the Hubble-Kurz calculation, but applied to these two-charge saddle solutions.
You don't mean like something as simple as Kerr-Newman, right?
No, Kerr-Newman, by I mean like F1P charges. Yeah, Kerr-Newman, if you embed in supergravity, it has 4 charges. You don't want 4 charges. Yeah, so you want only 2 charges. Okay. With rotation, yeah. So 2 charges with rotation, the solution is smooth on the horizon, but it's singular at the poles. And what these authors argue, it's that the singularity at the poles can be resolved with the higher derivative terms.
So what singular at the pole basically means it's not a coordinate singularity.
It's a real curvature singularity. Yeah. In the first paper we showed that it's a real curvature singularity at the poles. Yeah. Okay, so in 4 dimensions, so now in 4 dimensions, the BPS solutions are determined by harmonic functions on 3-dimensional flat base space. The harmonic functions determine metric everything. So the question is really, if you know the harmonic functions, then you know everything about the solutions. And what Chen, Murthy and Turiachi were able to argue is that although these harmonic functions change, but the 2 derivative equations remain valid near the poles. So harmonic functions will change, the changes will depend on the higher derivative terms, but once you know the harmonic function, you can construct the metric near the poles using the two derivative equations of motion. This was the main insight they gave. And then they gave some conjectural answer for the index, and they argued that, they gave a conjecture that it only gets contributions from the pole, but they did not know how to evaluate the index from the poles.
Is it correct to understand that the higher derivativeness basically changes the harmonic function?
Yeah, only changes the harmonic functions, but once you know the harmonic function, you use two derivative equations to find the geometry near the poles. Okay, so since we do not know anything about the solution anyway away from the poles, it is still difficult to proceed, although these authors gave very useful insights. For one thing, we still do not know where to compute this walled entropy. And we also do not know how to compute the angular momentum, because the formula requires not only the walled entropy but also this piece. What this paper is telling us is that there is some corrections at the poles, but beyond that they are not telling us anything about how to compute the angular momentum. Okay, so this is where off-shell black holes come in. So the idea is the following. So on GRQC, there is a growing interest in studying properties of metrics without using equations of motion, similar in spirit to what Nilay was talking about. Several authors have analyzed metrics based on just smoothness and laws of black hole mechanics. And in particular, people have studied rotating black holes in Boyer-Lundquist coordinates. So if you restrict some of that literature to Euclidean and BPS metrics, then this is how those metrics look like. So there is a WOF vector which comes with the t and phi term, and then there is a base. The base is flat, but since this base you want to write in Boyer-Lundquist coordinate, it looks a bit funny, but this is just a flat metric. Okay, A is the standard rotation parameter in the rotation. Okay, so one of the very interesting results that came out of this literature is that was shown by these authors, Baines and Weiser in 2023, that if you want the metric to be smooth in the Boyer-Lundquist coordinates, then you must require that the partial derivative of omega, partial theta derivative of omega is exactly 0, and this is 0 everywhere on the horizon. So let me repeat. So a general metric can be written in this form without assuming any equations of motion, and then you demand that this metric should be smooth, and that gives you a condition that partial theta omega phi must be 0 everywhere on the horizon.
That means omega phi constant.
On the horizon, yeah. So now if you combine this observation with Chen, Murthy and Turiachi, it allows you to make a very big jump. Since del theta omega phi is 0, and Chen, Murthy and Turiachi taught us that two derivative equations are valid near the poles, so we can find omega phi near the poles, and we know that once you have found omega phi near the pole, it is valid everywhere on the horizon. And near infinity, two derivative equations are valid again, and since you know omega phi, you can also use this to compute the angular momentum. So this is the insight we got from Chen, Murthy, Turiachi and the off-shell black holes. So our aim was to compute S walled plus 2 pi ij. What we are able to compute is the area of the black hole and the angular momentum, but there is this beast which is we still do not know how to compute. The area of the black hole turns out to be proportional to omega phi, so that's why this part is easy to compute, and this part is related to omega phi, so this part is also easy to compute. So you see, we are in one shot we are able to compute many pieces, but still there is this red piece which we do not know how to compute. No, they made a conjecture. Yeah, they made a conjecture based on Dhabulkar's 2004 paper, because they know the answer for the BPS black hole, and they sort of have some insight that the contribution will come only from the poles, so they made a conjecture for the.
Also make the same assumption in terms of the conjecture? Or?
No, we give a proof of the conjecture. Proof of that conjecture. Yeah. Yeah.
I'm a little confused about here. It looks like you have two derivative equations for this, and but omega phi, it's not fixed as an integration constant or something? Because you have to know the actual value.
Yeah, we have to know the actual value. So it is a constant, but that constant can be fixed using the harmonic functions. Yeah.
Sorry, but you give a proof in the sense you go ahead and make that correct assumption, compute and show it's equal to
Yeah. But the computation is very crazy. So the first part of the computation is this realization that omega phi has to be constant, and for a black hole, omega phi is fixed. No, I mean omega phi is generally proportional to sine square theta. So that kind of thing. So we're going to fix the constant. Okay, so now, but this was not enough. We still do not know. The area calculation told us that we don't need to know about the full solution. There is a possibility of computing the full walled entropy just by knowing what we know. And formally, this goes under the name of equivariant localization, which was developed by these authors in the supergravity context in 2023. So this paper and several follow-up papers gave a number of examples for computing the on-shell action, but no one has attempted computing the walled entropy. Okay, so let me explain what the general idea is. So consider a general black hole in Boyer-Lindquist coordinates. The walled entropy is some integral over the horizon, and no matter how complicated the black hole is, the integral is expected to be something of this type: f of theta times sine theta d theta d phi. We do not know anything about this function f of theta. So the question is, can this equivariant localization be used? Okay, so this is the localization in really the simplest possible setting. We do not know anything about the function f of theta. There is no hope of knowing of this function. But if it turns out that using equations of motion of gravity or whatever, if it turns out that f theta sine theta is a total derivative, f theta sine theta is del theta f of theta, such that the function f of theta at the poles can be computed using the near pole analysis of Chen, Murthy and Toriachi, then we are done, because then we know how to compute this. Okay, and this is what we are able to do. So this comes from this paper.
You want to show that it's a total derivative.
F theta sine theta must be a total derivative, and not only a random total derivative, because in one dimension every function is a total derivative. That function we should be able to calculate using Chen, Murthy's, Toriachi's analysis at the poles. That is the okay. So Dewitt et al. Gave us formulas for doing this. So we need to know more about the properties of the solution in order to implement this idea. So in a truly remarkable paper by Cardoso, Dewitt, Capelli and Mahopt, this paper, I was introduced to this paper when I was a PhD student, but for 25 years I could not make use of it. Only discussing with Ashok, I was able to make some use of this paper. So this paper did the relevant analysis. This paper does a mix of off-shell and on-shell supergravity, because they are interested in constructing some properties of solutions, and they gave us the relevant equations which we can use. So how this is as follows. So what this paper does is that this paper studies a class of half BPS stationary solutions in n equal to 2 theory. Residual supersymmetry and the subset of field equations are used to obtain the full class of equations that these solutions will satisfy. And a truly remarkable feature of this paper is that in the presence of higher derivative interaction, the Lagrangian is very cumbersome, and I mean, if you gauge fix the theory to Poincaré theory, then it's really very horrible theory. But in the way they do the analysis, all equations only receive minor corrections in the presence of higher derivative terms. So this may seem rather surprising, because the higher derivative terms are very complicated, but the paper is organized in such a way such that at every step you only get minor complications. And the two reasons they are able to do this is first, because the higher derivative terms are not the most general. They are the ones which are nicely encoded in this holomorphic prepotential function. And the second reason is that they are able to do this analysis consistently. They are able to do this in such a way such that at each step they maintain electromagnetic duality. So when this paper was written, I mean, it was just very curious set of results. No explicit example can be done, and I mean, the paper has many citations, but really no useful use of that paper has been made till now. But for our analysis, we were able to show that if one looks at S walled minus A by 4, it turns out to be total derivative in exactly the same way as required. Okay, so let me give a very small example of how this works, and then I will end. So let me give an example from a very small piece. So this was the Lagrangian, and this was the walled entropy, and this many terms. So I want you to focus at only one term. So let's say this one. So let's focus on this term. So we know what the Lagrangian is. So in the Lagrangian, this C hat will appear somewhere. We take the derivative with respect to the Riemann tensor, it will become some complicated object. This complicated object, some definition of this will be given in some supergravity paper. So they will give like some definition that this is modified supercovariant curvature tensor for Lorentz symmetry or whatever. I mean some definition they will give. Yeah, curly M. M.
It's just something that multiplies with the index structure is. Isn't that what that is?
No, this curly Rm is some sort of Riemann curvature tensor, and M refers to Lorentz symmetry. So it's a.
Lorentz symmetry is fine, but I'm saying that, but it is some kind of a tensor structure that multiplies the Riemann tensors that it is.
It's self-dual.
Just to get the
Some self-dual projection of Riemann tensor, something of that type. Yeah. The key idea is that the superconformal tensor calculus will tell you what this object is. I mean, if one learns, the bottom line is really this, that the superconformal tensor calculus will tell you what these symbols are in the Dewitt paper, and Dewitt paper will tell you what the values of those symbols are for half BPS stationary solution. That's how the whole paper is written, because these were the authors who developed the n equal to 2 supergravity. So they just tell you the values of various symbols for half BPS stationary solutions. Okay, so when the dust settles, one finds that just with that term, the answer looks something like this. So you get some total derivative, which becomes some calculation at the north pole, some calculation at the south pole, and then you get some prefactors in front. So I have already argued that omega phi was a constant at the horizon, and if we work with a theory where imaginary fa hat is a constant, then you can see that the localization has worked, because this is some quantity which Chen, Murthy, Turiachi will tell you how to compute at the pole. So one computes these numbers and one multiplies with these numbers, and you will get the answer. So the idea is worked for the case of imaginary fa hat equal to constant, and hence the near pole analysis completely allows you to fix G and omega phi, and this way we can compute the fold wall entropy. Okay, now there is so this is really the case where there is only this piece, but in general there can be, because there are more terms here, so one has to worry about these other pieces also. But this is where the new attractor mechanism comes in. So the new attractor mechanism tells us what the values of the scalars are at the poles of the saddle. The answer turns out to be the same as the old attractor mechanism, and that's why Chen, Murthy and Turiachi were able to make this guess or the conjecture. And once one uses carefully the new attractor mechanism, one finds that indeed the Wald entropy plus 2 pi ij, the expression exactly matches.
Just get this straight.
Yeah.
Whole attractor mechanism, you mean to the quantum entropy?
And the classical entropy function.
Entropy,
Yeah.
You take the attractor, you get the
value of the scalars at the horizon and the area of the sphere. Yeah. Size of the S2. Yeah.
The entropy function for that.
Yeah.
Okay, so that's the old.
Yeah.
And why couldn't you have done that in the first place?
Because the saddle has no ADS2 times S2 region. The saddle is a non.
So then how would you, when you say the answer is the same as old attractor, I'm a bit confused.
Because we believe that the entropy is same as the index, and the new method is telling you how to compute the index. So now we are showing that index is indeed equal to the old answer.
Okay. You mean the old answer would have given you the entropy?
Yeah, old answer would have given you the not the index.
Now I'm getting it.
Yeah.
The new thing allows the direct computation of the index.
On the gravity side. Yeah, on the gravity side. That is the. Yeah.
Just one thing, please go. Didn't Ashok have some arguments that entropy must equal index?
Those arguments require factorization. Those arguments require factorization from asymptotically flat region to ADS2 times S2 region. But the new method does not require any of that. New method allows you to do the calculation in the asymptotically flat region.
Okay, so
Yeah.
isn't it fair to say that you could have argued on the basis of Ashok's result anyway that the entropy equals index, therefore it is a calculation.
Yeah, so partly, but there is also this issue that Witten index is independent of the size of the circle that you will use in doing the computation, the size of beta, and that one would not be able to argue based on the old Ashok's argument. So for that one needs a new calculation. Okay, so that's all I wanted to say. Is so as you can see, so the theory was complicated. These authors gave us some insight. Then we needed more insights. Then we got some hint that this is something like localization. Then this paper allowed us to do the localization exactly. Okay, so now conclusions. So we were able to show the matching of the old world entropy with the index. The new calculation required computing the world entropy of the saddle plus the angular momentum. For an arbitrary single center half BPS black holes in n equal to 2 theory. We still do not know much about the saddle solution. We only know some of its property at the poles, that's all. But that's all we need to do this computation. Our work crucially uses the supersymmetry analysis of Dewitt et al. Paper. This paper is really very complicated, but as I said, I was introduced to this paper 25 years ago, and it has been on my on my mind for many years, and we were able to do something with it. Okay, so future directions and some comments. So more examples. One would like to construct more examples for this saddle solutions in 2 derivative theory or possibly in higher derivative theories. So in 4 dimensions, number of people have written many examples, but in 5 dimensions, only recently people started exploring. So we gave some set of examples, and just last week there was a paper by Emparan and Samir Murthy where they gave more examples. In STU model, we are working on with these authors, and I am hopeful that one can construct saddle solutions for the simplest zero area black rings, but I do not know. I mean, this is something I've been thinking about for more than a year, but I do not know whether we can actually do this. Okay. So in the paper that I presented, we did the analysis in the Lorentzian signature, but as many of you pointed out, we have to do this analytic continuation to complex angular momentum. Actually, it will be very nice to do this analysis in the Euclidean n equal to 2 supergravity, which is another beast. But we hope that this calculation is doable in that setup. If we do the calculation in the Euclidean n equal to 2 supergravity, then there is a very high hope that we will be able to generalize this calculation to 5D with higher derivative corrections. So far, all the discussion has been computing the gravitational, computing the indices from the gravitational path integral point of view, but there is a very big subject of computing twisted and twining indices and exploring subleading saddles. Almost nothing has been written on this subject on these things. Finally, a formal understanding of the relation between the old and the new attractor mechanism is much needed. There is some understanding based on what has been written, but more clear understanding is required. Okay, so with this I will stop.
Yeah. Lots of time for questions.
Yeah.
Sorry, thanks a lot.
Yeah.
Just about your last point, I thought Ashok's argument roughly was, but please correct me, was that you have an SU2R symmetry in the n equals to Ks, and that was tied to the spherical symmetry.
Yeah.
In the
Yeah.
And from that he argued that therefore the full index, the full entropy would be there.
Yeah, so the argument was that because of this non-abelian symmetry, the contributions coming from fermionic excitations is 0. So this index only get contribution from the bosonic part, and hence it is equal to the entropy. So this was the argument. This is the near horizon argument. Okay, but
do you think that argument is incorrect?
Yeah, this argument has 2 catches. One catch is that there are what are called Hare modes. So there are black holes admit Hare modes which sort of start from the near horizon region and go to asymptotic region, and these Hare modes do not allow this factorization to happen. One cannot factorize the near horizon ADS2 region from the asymptotic region. So unless one knows exactly what the contribution of Hare modes are, one cannot say that one cannot say that the entropy is indeed computing the index, because index was computed at, in some sense, at infinity. It was computed using the brain systems. So the index is computed at infinity, but Hare modes have to be accounted for. So actually Yogesh will give a talk on the Hare modes. Yeah. So just sorry, 1 second. Did I answer your question?
I'll ask you more later about
Okay.
why
So this is one comment, and the second, what I said earlier about the temperature independence. The index is supposed to be temperature independent, but that physics doesn't come out in Ashok's calculation.
come out, but I mean the question is there a formal flaw in the argument?
Yeah, apart from this Hare mode, I don't think there is a flaw.
I want to talk about that factorization with you later.
Okay.
And let others
I just want, there are 3 ingredients in it that you used in
Yeah.
the calculation, right? So the third ingredient, can you just roughly give an idea how it was useful? It was
Oh,
the complicated paper that you mentioned.
Yeah. So what this paper does is, so what we are looking for is rotating black holes in higher derivative theory, higher derivative supergravity theory. There is no hope of solving those equations. Those are really complicated equations. But what this paper does is that it writes these equations in a very manageable form. And once one uses those equations with the answers for the metric, it turns out that the term that you need is actually a total derivative.
So from what you said, it's not clear that that would work, but it turns out.
It turns out that it works. Yeah. And the hint for this comes from these papers, because these papers also use something very similar, like they write down a 2 derivative theory with very complicated d equal to 6 supergravity or whatever, and they show that if you want to compute the entropy of a black hole in this theory, it turns out to be just getting contributions from the poles. Yeah. 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 Yeah.
But in this formalism, it is all wild tensor, I believe.
Yeah. So yeah, exactly. So this is a bit of a puzzle for us. With these 3 authors, we have done the example for the STU model, but now what we are struggling with is precisely this question, that if we do not know the supersymmetrization, can we still use the relation between old and a new attractor mechanism to compute the answer using just Gauss-Bonnet? One has to make some assumptions for sure. We are trying.
Total derivative, the fact that total derivative relies on the fact was like wild tensor.
No. It only relies on some very n equal to 2. Yeah, supersymmetry analysis was very important. Yeah.
Let me come back to this factorization if you don't mind. Because you're including higher derivatives, but of course we're doing classical gravity.
Classical gravity.
In the end, you're computing an on-shell action.
Okay, no, this was really Ashok's key insight. Ashok from day 1 kept on telling us that on-shell action calculation will not work, because on-shell action calculation is, one has to do in Poincare supergravity, and Poincare supergravity from this superconformal theory will be very difficult to obtain. So he kept insisting that we should compute the Wald entropy. And indeed, but you're right, in some sense Wald entropy is related to the on-shell action, but on-shell action way of doing this calculation most likely is not workable.
But the Wald entropy is of course just defined at the horizon, right?
Yeah.
No, I was going towards your point about why the factorization becomes an issue. Because if you're going to use Wald entropy, then you're working in the near horizon region. And
No,
you
no.
just have, what is the argument?
The saddle has no near horizon region. The new formula, this Murthy Turiachi formula, tells us that index is equal to the Wald entropy plus 2 pi ij, and there is no near horizon region there.
I'm an old guy, so I'm trying to use the old formulas. That's the divide, sorry.
Okay.
I'm just trying to understand what was wrong in the older argument, and your answer seemed to be that there's hair and the answer doesn't factor.
You can think of it like this.
Yeah.
Old answer, there was a confusion between what is index, what is entropy. The new formalism tells you how to compute the index.
And you didn't like Ashok's answer, the old answer by index equals n.
Yeah, I mean it's partially, it gives partial understanding. It does not give full understanding, because Hare modes, we don't know how many Hare modes are there. Hare modes can give rise to a lot of contribution to the index. Actually, as shown in one of the papers by Justin, in some cases Hare modes give a lot of contributions. So
You separate the, I thought you could separate it out.
you can separate if you know all the Hare modes, but in
Higher derivative.
Yeah, this is also.
So you say you don't know all the high.
I mean, we know some hair modes, but we do not know all.
Yes.
But this calculation is really index equal to index. Index on the microscopic side and index.
Nothing against your beautiful calculator. It's a Jordan course. The earlier one is something mere mortals.
Actually, when I was younger, I thought the old calculations were really very difficult, and now we are able to do the new ones.
One last question from our side.
Yeah.
It's probably a very stupid question. So
Yeah.
I don't quite understand how one should do this analytic continuation to the complex. Are there explicit values known on which?
No, actually the rules of that game is not fully clear. For two-center solution, there is a reasonable guess for how to do the analytic continuation, but for black rings or for four-center solution, it is absolutely not clear how to do it. So this is one of the reasons we are interested in generalizing all this to Euclidean supergravity, so that then we don't have to rely on this analytic continuation rule.
In the cases when it is known, do those complex geometry satisfy the group condition?
They satisfy those Witten's complex geometry conditions. They satisfy that, yeah.
Let's thank Amitabh.
Okay, thanks.